In this video, we are now going to put our different circuit elements into the same circuit hooked up to a AC power supply. Now we are going to only do this for series circuits, where the circuit elements are wired in series with the power supply. You can do this with parallel circuits, but for the sake of time, we're only going to focus in on series circuits. Because we are in series, that means that the current is the same through each circuit element, and that the instantaneous voltage across each circuit element has to add to the instantaneous voltage from the power supply. So that is energy conservation. You can't lose or gain energy as your voltage drops across each circuit element. Alright, so I've drawn down below a phasor diagram showing the current, and the voltage across the resistor is going to be in phase with the current, while the voltage across the inductor is always going to lead, and the voltage across the capacitor is always going to lag. And notice we have two 90-degree angles, so these are 180 degrees from each other. And then this is going to be the voltage from the power supply, and there's an angle, what's going to be the phase angle, between the current and that voltage. Now keep in mind, these are phasors and not vectors. So technically speaking, this entire diagram is rotating around and around and around and around as time progresses. But it's all staying in lockstep with each other. So we can sort of treat it like vectors in order to set up some relationships in order to solve for different aspects of this circuit. So the first thing I'm going to do is take advantage of the fact that the voltage across the inductor and the voltage across the capacitor are 180 degrees from each other. So if I add them together, because they're along the same line, so I'm allowed to do that, I end up with a vector that is VL minus VC. Now I've set this up so that the voltage across the inductor is greater than the voltage across the capacitor. It'll work the other way around, but we're just going to set it up this way. You're going to find out when we do this we square something, so whether the subtraction is negative or positive doesn't actually matter. And then I'm going to draw my other red vector, really the same thing as the voltage across the resistor. I'm just drawing it smaller so you can continue to see the blue line. And these are 90 degrees apart from each other. So this is the same thing as the sides of a right triangle. So I can say that the voltage across the resistor squared plus the subtraction, because they're 180 degrees apart, of the voltage across the inductor minus the voltage across the capacitor squared, I could take the square root. And that should equal the hypotenuse of the triangle. And so remember, the sum of the voltages need to equal out to the voltage from the power supply. So by doing this vector addition, I'm adding together my voltages across each circuit element. That should then sum to the voltage from the power supply. Alright, so we can take this a step further, and I can rewrite all of my voltages here. So this would be I times R squared, and then we would have the current times the inductive reactance minus the current times the capacitive reactance, and that's squared. So since all the currents are squared, I can factor them out. And we're starting to see something that shapes up to look like Ohm's law again. So we're going to rewrite Ohm's law to look like this, where Z here is going to be the impedance. And it's once again going to have units of ohms, so you can sort of think of it like the resistance, the equivalent resistance of the circuit. And then your impedance is going to equal R squared plus the subtraction of the two reactances squared. So you're going to maintain that sort of Pythagorean theorem looking shape to that equation. Now I need to be able to find this phase angle here. So what I'm going to do is I'm going to move where VR is in this diagram so that we have a more traditional looking component method diagram. So VR would be here, so this would be VR. And this here would be the angle we would normally find. But we want this angle over here, so this angle plus that angle is equal to 90 degrees. So I'm going to redistribute and say this phi is the same as this phi down here. And so that allows me to do opposite, which is going to be our subtraction here, and adjacent, which is going to be the voltage across the resistor. So that means that the tangent of our phase angle is going to equal the inductive reactance minus the capacitive reactance, and I've just canceled all the currents out, divided by the resistance. And keep in mind that this relationship is in radians. Now I do want to clarify one thing here about the statement about the addition of the instantaneous voltages adding to the instantaneous voltage across the power supply. The instantaneous voltages are going to be the algebraic sum, so you can add the instantaneous voltage, so little v's, across the inductor, the capacitor, and the resistor, and that should sum to the instantaneous voltage, or little v, of the circuit. In order to add together the maximum voltages, you have to do it using this vector addition that we've set up here in this video, because the maximum voltage across the inductor is not happening at the same time as the maximum voltage across the capacitor, so they're not in phase with each other. So if you add them together, you're not going to get this V. In order to be able to add them together, you have to add them together taking into account the shape of this phasor diagram that we've drawn here, which is why we've done it using vector addition, because taking into account that how one leads and one lags and one is actually in phase with the current, it allows us to actually be able to establish the relationship between the maximum voltages and the maximum voltage from the power supply. So you have to keep that in mind. The instantaneous voltages are an algebraic sum. The maximum voltages are a vector sum because they're not in phase with each other. So you have to take into account that fact that they're not happening simultaneously, or else it looks like you have way too much voltage and it doesn't equal out to the max voltage. The last thing I want to do in this video is to draw the circuit diagram for you. And the big reason why I want to do this is to familiarize yourself with the symbol for an AC power supply. So this is a symbol for an AC power supply. So it's very important that you know that, so that when you look at a diagram on a homework assignment or on a test or a quiz, that you can establish, is this a AC problem or is this a DC problem? So you need to know that difference between a DC power supply symbol and an AC power supply symbol so that you can read your circuit diagram correctly and apply the appropriate relationships.